Good evening, all. Welcome to the final session of live sessions for Computational Fluid Dynamics of Incompressible Flows. And today is mostly going to be a summary of whatever we discussed up until now. And if you do have any questions, we can also discuss those questions. So this will be the last session for this series of lectures. So we started out this particular course from deriving the governing equations for fluid mechanics, where we have continuity equation as del dot u is 0. We are only discussed for incompressible flows, or in general, we'll have the material derivative plus rho times del dot u is 0, where the material derivative is given by the normal time derivative plus whatever the quantity you have, you just did. So this is the, and then we discussed about Lagrangian versus Eulerian and all of that stuff. And then we have the momentum equation. We have x momentum equation given by, or in general, du dt. Then mu del square u, the pressure gradient term, plus we also have the gravity term. And then we have the energy equation. Again, we have a diffusion term. Plus, we also have viscous dissipation term, which is applicable only when you have high speed flows. So, and then the general scalar transport equation is also something we started out with. Where we have a scalar phi that is being transported because of advection. So then the governing equation becomes d phi dt, or I'll just write the equation, the one which we will use later, rho phi plus the advection component should be equal to the diffusion component plus some source terms for that particular scalar source. So these are the different equations we derived with. It is where we started out with. And of these equations, how to solve these equations and is what we discussed throughout the entire course. And the first step towards that is understanding what these different types of equations are. All of them are partial differential equations. So first we started out with identifying what a partial differential equation is, where you have a function which is a function of multiple variables, and then we are trying to take a derivative with respect to one or more variables. So we have a partial derivative here, here, everywhere. We have like all of these partial derivatives. So we started with the different classification of these PDE. So general PDE in a second order PDE can be written as something of this sort. And then you have the all other terms with respect to phi x, etc. so on. So let's say I call all of that as t. So if I have a general partial differential equation of this particular form, which is second order, then we try to define something called a characteristic line. So say if I define, like I want to convert this into one parameter and I want to kind of solve this equation. So before solving the equation, we want to understand what is the nature of this particular PDE. Then we define something called discriminant as basically b square minus 4ac. And then we classified this as it can either be positive, negative, or equal to 0. And for each case, we have a different class of PDE. So if it is positive, we call it a hyperbolic. If it is negative, we call it elliptic PDE. And for the other case, we call it as a parabolic PDE. And the basis for this classification, you can start by saying, say, y equals to some eta x, and then do the substitution backwards. So you can, if y equals to eta x, or basically the other way, or eta equals to y by x, then I can write all these equations in a different form. So I can write phi x as basically phi eta times eta x, and so on. And once you do this substitution, you will eventually end up with the equation of the form, so, which is basically phi eta. Eta x is minus y by x square So this will be minus eta phi eta 1 by x. If I do a derivative again, so that will be minus eta phi eta 1 by x into again eta x, so that will then be another minus 1 by x into eta. So this will give me eta square by x square phi eta. Similarly, phi y to eta y, phi yy will be eta into 1 by x square. Phi yx or phi xy, either way, will be, let's say phi yx is something we start out with. If I take a derivative here, so that will be phi eta into eta x into 1 by x plus or minus phi eta into 1 by x square. So this will be phi eta minus eta 1 by x square and so on. So you can substitute this back into this equation, then you will eventually reach a form of this kind, a eta square plus or minus, I think minus, it will come a minus b eta plus c, something of this particular sort, times phi eta and so on. So other terms will come. And what we are trying to understand is this is a PDE, so which terms are significant in this? So this, when this equals to 0, depending on how many roots you have here, this will be the characteristic equation of that particular line. So we got y equals to, if you have two roots, then it will be y equals to eta x, y equal to eta 2x. These will be the characteristic lines that I will be using to solve the equation. So if it is an elliptic equation, you will have this less than 0, which means you will not be able to separate this into two different points. So you will not have any characteristic lines, which means that information propagates in all the directions simultaneously. In parabolic, we'll have only one solution, so that will be the one direction in which information propagates. That is what we discussed initially. So these are different classes of PDEs, and from which we understood what characteristic lines are, and then we decided, okay, each characteristic line like decides how the information propagates. So if there is an error in your solution, so in all of these are kind of, we usually deal with nonlinear PDEs. So the strategy to solve a nonlinear PDE is you assume something, and then there will be some error, and you try to reduce error in every iteration. So how the error propagates through the solution is what we will be interested eventually in. So depending on the class of problem, the propagation will be different. And this is with respect to the classification of PDEs. Once we know that how to classify the PDEs, we understood, okay, there are different problems. So examples for each of these problems is what we discussed next. So for an elliptic problem, the example is, as I said, information has to propagate infinitely. So steady conduction is an example of elliptic problem. Steady state heat conduction in some slab or any domain is an example of elliptic problem. Parabolic problem is where you have information propagating only in one direction. Just a boundary layer is an example of parabolic problem. Hyperbolic is one where you have two different characteristic lines. So all for Mach number greater than 1, all flows are this thing. Wave equation is an example of hyperbolic equation and so on. So to write the equation, so for elliptic you have, just to show an example. So if I have an elliptic equation as uxx plus uyy equals to 0. So this is an elliptic equation. You can check here. B is 0, A is CR1. So if I do B square minus 4AC, that will be less than 0. So this is a steady state heat conduction equation, which is an elliptic one. And then let's say parabolic, you have unsteady heat conduction problem, something like UT equals to some alpha uxx. So this is a transient heat conduction problem. So in this case, you have A and C are 0, and sorry, A is alpha, B and C are 0. So if I substitute B square minus 4AC, that will turn out to be 0. So this is an example of a parabolic equation where information propagates in one direction. And then for hyperbolic, example is wave equation. You have something like UTT is C square UXX or so on. So in this case, A is 1, B is 0, C is minus C square. So if I compute B square minus 4AC, that will be 4C square, which is greater than 0. Is that clear? So this is with respect to the classification and examples for each of the cases. Then we introduce something called a Taylor table. So we started out with finite difference method. So the idea is you have a PDE and then you have to find a solution for that particular PDE. And when we need to find a solution, the strategy is you have a domain, you have some function f. We try to discretize the domain. The first step in FDM is to discretize the domain. So that way you are not essentially solving for the entire function, but instead you're only solving for these values at known x. So since you discretize the domain, you would know all these values. So say this is xi plus 1, xi minus 1 and so on. So at each of these points you have the function values. So these f's are the unknown variables that we are trying to solve for. So if these are the variables that I'm trying to solve for, so how do we solve for each of these variables? So we need to know some equations, and how do I get the equation? The equation is what we will try to get from the PDE. So the PDE will be the equation, but the PDE is in its continuous form, so I have to discretize it first. So let's take an example for that. So let's take the steady state heat conduction problem. For suppose you have a variable like uxx plus uyy is 0. If this is my equation, so I have to convert it in such a form, or since I've used f here, we'll just use the same notation. So I have function fxx plus fyy equal to 0. Now I have to find these values fxx and fyy. So how do I do that? So if you solve a 1D case, for example, so I have something like this, and I want to find this derivative. Then we introduce the concept of Taylor series. So where we have Taylor series is you expand the function around any given point by delta x. So that will be given by f of x, and so on. So this will be order of delta x cube. Whatever is the remainder term, like the higher order coefficients will be there. So, but the Taylor in the Taylor table is used to construct different series like this. So first step is the table has certain rows and columns. So let's understand what the rows and columns are. So each column is basically the corresponding coefficient for this. So we have f, f prime, f double prime, and so on. Since we are only interested in f double x, which is f double prime, so I'm writing only till f double prime. Then each of the row should correspond to the coefficients that I'm looking for. So I'm trying to find f double prime, and what are the values of x at which I'm trying to find that is what these rows represent. So here I'll be doing fi, I'll use fi, the value at the current one, the value at the next, and the value from the previous one. If these are the three values I'll be using. So what I'm trying to do is I'm trying to write an equation where f double prime is given by some constant into fi plus b into fi plus 1 plus c into fi minus 1. So there will be some constants for each of these. And now if you do the Taylor series expansion for fi, because we are expanding around the same point, you only would have the term for f, and f prime and f double prime will be 0. Similarly, if I'm doing an expression for fi plus 1, I'll have f plus delta x. This will be delta x square by 2. Similarly, for fi minus 1, I'll have 1 minus delta x square by 2. Now what we have to do is I have three unknowns, so I need three equations to be able to solve for this ABC, and these equations will come comparing these coefficients. On the LHS, I do not have any term for f, so all I have to do is 0 is a plus b plus c. For f prime, I have no coefficients on LHS, so 0 is, sorry, b minus c times delta x. And for f double prime, I have a coefficient of 1 on the LHS, so 1 equals b plus c times delta x square by 2. So all we need to do is solve this set of equations, which will give me c, and if I substitute that here, b equals to c is 1 by delta x square, and A is minus 2 by delta x square. So my equation for f double prime is fi plus 1 minus 2fi plus fi minus 1 by delta x square. And the order of accuracy is whatever the terms that will be left after this. So this is the construction of Taylor table. So this is for one particular term. Now if I have an PDE like a phi xx plus b phi xy plus c phi yy and so on, each of these terms I can again construct a Taylor table like this and then evaluate all these ABC values and then create my stencil. So these coefficients are what we call as stencil. So we have this I minus 1 a plus 1 and so on, and then once we created the stencil, all we have to do is write the equations together and solve them. So that would be the next step. So before solving them, so since we discretize something, there are few other important concepts here. One is the idea of accuracy, stability, and convergence. So what we are doing now is, okay, we have an original function f of x, but what we did is we created a stencil and then we are approximating the value of a function between these values. So if I have an original function like this, I'm doing something like this. So I'm not using the original function value in between, but instead I'm kind of approximating, doing an interpolation between these two values. So depending on the way you discretize, this will change. So we have different metrics. So if I have a value y hat that I'm approximating, so y is my actual solution. So the difference between this thing is what we call an accuracy. This we already know. So in our particular case for Taylor expansion, so if I am trying to approximate f of x plus delta x, using the value, so at f of x, so if I have two nodes, so this is xi, this is I plus 1, and then I have some functional form between these two, and I want to approximate something in between, or I want to approximate the derivative of f of derivative of function at I, so on, whatever we are trying to do. Let's say we are trying to approximate f prime at xi. I do not know the function f, so I cannot calculate f prime analytically. So what we do in finite difference is, again, you construct a stencil. The forward stencil is fi plus 1 minus fi by delta x. This is a forward stencil. When I constructed this stencil, so there will obviously there will be an analytical solution for this value at an intermediate point. Let's say at any point x, there will be some analytical value. So how well will that analytical value be close to this value that I'm calculating here? So the value I'm calculating here, I'm assuming like I'm doing a straight line like this, and to any point in between, I'm saying it will have the same slope like this. So how accurate is this value compared to the analytical solution? The difference between them will tell me the accuracy. So from the Taylor expansion, we can do fi plus 1 is fi plus delta x times f prime plus delta x square by 2 times f double prime and so on. The higher order terms, I'll just put delta x cube. If I substitute this into the original equation, my f prime at x will be the difference of these two will be f prime plus delta x by 2 times f double prime and so on. So the terms, this is the analytical solution, but I'm getting extra terms here. This extra terms is what we'll call the order of accuracy. So how accurate? So all I have to do to reduce the error is basically reduce my stencil size. So if I use a smaller delta x, then both of these will be closer to each other. So the order of accuracy for this particular scheme is first order accurate. So let's say the power n, in this particular case n is 1, so it is first order accurate. In general, for different schemes, this will keep changing. All you have to do is do a Taylor series expansion around a given node and then obtain an expression of this particular kind. Then it will tell you the order of accuracy of that particular scale, stencil. Then we have the concept of consistency, which says that as you refine the mesh, the value that you are seeking and the analytical value will approach each other. That is what you call a consistency. So as delta x, in different cases you have delta t also. As they tend to 0, the analytical solution should match the discretized solution, or the discrete solution should match the analytical solution. Then you call that particular scheme as consistent scheme. And then we have the concept of stability. So stability is basically you, when you are trying to solve some particular variable, you keep iterating, as I said. So as you are iterating, if the error is not growing, so if I define epsilon as an error at an iteration step n plus 1 by the error at the previous time step. So this is what we call a growth factor. So if this value is less than or equal to 1, then you call it stable. So what we are trying to say here is error from one step to the next step will either remain the same or it will decrease, but it will not increase. If it increases, then we call it unstable. So stability is one more criteria. So there is this, if you remember, we had discussed Lax equivalence theorem, which says that if you come up with an algorithm which is stable and also consistent, which means as your mesh becomes finer and finer, you get a solution, your solution becomes more and more closer to the analytical solution, then you will say that that particular scheme will actually converge. So this is with respect to accuracy, stability, and convergence. Once we discussed this, we moved on to linear solvers. So what we understood from this is we have a finite difference equation. We converted it into set of equations that we will be solving for, set of simultaneous equations. And the first step that we started out with is uh, an equation of elliptic nature. Let's say something like this. Then when you discretized it, you will get an equation like ui plus 1. So this is basically a set of linear equations. If you have a function f here, then accordingly this will be fi. So this is basically a linear equation. So if I were to group the terms together, so I'll have minus 2, 1, 0, 0, 1, minus 2, 1, 0, 0, and so on. This will be some matrix times u is some matrix f. So this is basically something of the form ax equal to b that we are trying to solve. So all we need is a solver here for this particular system of equations. We discussed different methods. We discussed direct and indirect methods. The difference between them is how so direct methods will actually solve the solution till whatever is your accuracy of your computer, whatever is that floating point accuracy you're using for your computer. Indirect methods is like you set a threshold and then you reach the solution there. So the how do you reach a solution is basically you start with there are again we discuss different techniques. So direct method we discussed on like you know the direct methods, basically it will be like a inverse times b, but then we don't calculate a inverse b. We use some kind of structure within the matrix and to our advantage. So one such algorithm is TDMA, which we discussed extensively. The idea in TDMA algorithm is you are expecting the matrix A to have certain kind of a structure. So TDMA stands for tridiagonal matrix algorithm. So you are expecting your matrix to have a tridiagonal nature. So it means you have all the diagonal elements and plus and minus one of diagonal elements and everything else is zero. When you have matrix structure of that particular sort, then your governing equations will become something like A phi will be something times pi plus 1. You only have one off diagonal plus and one minus off diagonal. So you'll have ci phi minus 1 plus di. So this will be the type of equations you will be solving. And this is something that will keep coming as we see later also. We have already seen that. So how do we solve this set of equations is uh, there is some tricks to solve this equation. So the idea is people who are familiar with LU decomposition might already know this. So ax equal to b can be written as ux equals to b, and this will simplify as if I write ux equal to y, all I have to do is first do the LU decomposition. Once I have the LU decomposition, all I have to do is get the y, which is u times x, and then all I have to do is solve for these equations Ly equal to b. Once I have the lower trigonal matrix, this equation is straightforward. So I will reduce the number of iterations I have to do for the Gaussian elimination method. Or if you are familiar with the TDMA, which these are equivalent in the sense. So you can also write this basically as phi can be written as some pi times pi plus 1 plus qi. So what if you see what I'm trying to do here is only so this is the equation we have. So we are trying to find there will be an upper triangular matrix times x which will be y and lower triangular matrix times y which is equal to b. So this is basically writing it as an upper triangular matrix. So I can also write this as pi minus 1 is 1 times pi plus qi minus 1. I can substitute phi minus 1 into here. Then I will have an equation between phi and phi plus 1. Then compare these two equations. From there I will get expressions for pi and qi. Then I have to do iteratively. So I'll start from I equal to n and then keep doing it. So that is Thomas algorithm. That is with respect to the direct method. And then the most important, or the one that we usually use, is indirect methods. In indirect methods, the idea is to start with some guess x naught, and then you keep updating it. So we discussed Gauss-Jacobi. So you have a set of equations, something like AP Phi sigma A and B phi and B. These are my set of equations that we are trying to solve for. So in Gauss-Jacobi, what we will do, we will start with some initial guess, and then what we will do is we will update it something like AP Phi n. The next iteration value will just be whatever summation I have taken from the previous iteration values plus b. So this is a simple Gauss-Jacobi iteration. So we will keep the phi values constant and then we'll move to the next iteration. But then there is a Gauss-Seidel method where we will keep updating all the values simultaneously. So we discussed these two methods also, and we also discussed that these methods have certain disadvantages in terms of that, because as you're iterating they can diverge. So in order to ensure you have stability for that particular algorithm, and that stability will depend on the condition number of this particular matrix A, we introduce the concept of relaxation, where you can either speed up your convergence or kind of increase the stability by either under or over relaxing it. So if, for example, x is the solution you got from Gauss-Seidel method, the next value of xn plus 1 you will take as from the previous iteration. So this is from the previous iteration value. This is the Gauss-Seidel update that you are getting, what the Gauss-Seidel algorithm tells you. So you use a weight combination of these two values, and depending on the value of alpha, it can either be over or under relaxation. And we have seen how to identify these values for different problems that changes from problem to problem. There are some values that are already been discussed in the lecture video. So this is with respect to the linear solvers. Then we moved on to parabolic and hyperbolic equations, where the concept of stability is much more important because we have to do the time marching. When we are doing time marching, as the time progresses, the solution should reach a stable value, so the error should not grow. So there we again introduce this concept. Let's say this equation something like del phi del t is some c times del square phi del x square. Let's take a parabolic equation, or we can start with a hyperbolic equation that will be even easier. So phi dt plus c square times 0. Let's say I have a hyperbolic equation of this particular kind. Then we can do different kinds of discretization. So in the time domain, I can write the double derivative, or let's say parabolic is easy, I think. It will be easy to understand. Let's take a simple equation like this. This is also hyperbolic anyways. So if you have an equation of this particular kind, then the time derivative can be written as phi n plus 1 minus phi I n by delta t plus c times px can be written as pi plus 1 minus phi minus 1. Both I'll evaluate at time step t, which is n by delta x equals to 0. So first you write the discretized form of the equation, and then what we are trying to do is we are trying to understand how the error changes. So the error can be written something as e power a times t times e power ikx. So error will vary as a function of time and t, and then we discuss something called growth factor, which is basically e power a delta t. So if I substitute n plus 1 n, so if I substitute the equations back here, so I have n plus 1, so there will be e power a delta t here. There is I and n, so there will be just 1 here. Plus I can take c delta t by delta x. Maybe I should have written minus here. It doesn't matter anyways. Then we have n here, so the t gets cancelled, and wherever we have I plus 1, so we'll have e power I k delta x, minus we have minus here, so that will be minus I k delta x. And we are interested in finding this value, which is g is e power I minus this one will be minus 2 c delta t by delta x times, sorry, this will be something like this. And what we are trying to do is understand whether this growth will increase or decrease with respect to this value. So, and as the error is basically a function of time and space, we want the error growth, whatever growth we are saying, should be independent of the wavelength we are choosing, because we do not know what the wavelength and like the error wavelength could be anything. We do not know it. So for this should be true. We need modulus of g to be less than 1 for all possible values of k. And for this particular function, for that to happen, should be less than 1 or less than or equal to 1. From there, we'll get the criteria that delta t should be less than or equal to delta x by 2c or so on. And so on. The basic idea is the same. So you have the equation, the differential equation, then you do the discretization first. Once you do the discretization, then you assume an error of this particular form, then get an equation for the growth factor. And then what we are trying to do is try to find a criteria that satisfies the growth factor less than or equal to 1 for all possible values of k. Once you do that, you will get an criteria for it. So different algorithms will have different criteria. Some algorithms will actually tend like any value of k you choose, this will never be satisfied, so they are unstable. If there are certain values of k for which this is satisfied, then also it is unstable. We need to make sure that this is less than or equal to 1 for all values of k. There will be some algorithms which will satisfy this for all values of delta t and delta x. So those are the algorithms which are unconditionally stable. If this is true for all k, delta t and delta x, then we call those algorithms as unconditionally stable. You can have mod g greater than 1 for all values of k, delta t, delta x, or for even some values of k, delta x, at least 1k and all delta t, delta x. Then you call that particular algorithm to be unconditionally unstable. Hi, I'm going through a quick summary of whatever we discussed. If you have any questions, we can stop and discuss that also first. Okay. After the stability analysis, we discussed the vorticity stream function formulation. So where we have, let's say 2D, this is applicable only for 2D flows. So we have our governing equations. Again, this is for a study case. Because it is incompressible, rho is constant. The reason we started with this vorticity stream function formulation is because we have three variables, u, v, and p. So if I write the equation for y momentum equation, plus the viscosity term. We did not discuss the natural convection problem, so we do not have any body force terms. So with these three equations, I have three unknowns, u, v, p. So what we do in vorticity stream function formulation is we try to reduce the number of equations by reducing the number of variables. So we made certain assumptions. So we defined two other variables, psi and omega, where psi is the stream function such that your u will be given by psi y and v is given by minus psi x. And we define omega as del v del x minus del u del y. So when we define like this, if you substitute this equation into the continuity, ux plus vy will be psi yx minus psi xy, which is 0. So continuity equation is satisfied by default. And if I do the same thing for omega, so all we have to do now is a little more rearrangement where you do del u del x again, etc. All these terms substitute into this equation. So we do, let's say this is equation 1, this is equation 2. So we try to take the derivative with respect to y for equation 1 minus del x of 2. If you do this and little arithmetic, then these two equations will get reduced into one more equation, which will be something like u times del omega del x plus v times del omega del y is nu times del x square. So this will be the equation we will be ending up with. So the main point here is the term with respect to pressure is completely gone from this equation. So now we have u and v, we can substitute the values that we have. U is del z del y del omega del x. Sorry, v is minus del z del x del omega del y is nu times del square omega del square x plus del square omega del y square. And then we have one more equation, which is omega is given by del v del x is minus psi xx plus psi yy. So this will be the two equations that I will be solving now. Instead of the three equations, now the problem is reduced to two variables and two unknowns that we will be solving, like two unknowns and two equations that we will be solving for. So here again, we can use a Taylor table, get an forward differentiation with respect to y, x, all these things can actually be done very easily. You can use a central difference stencil. You can define a stencil and get all this in second order accurate scheme, and then you can solve for it. The only challenge with this method is the boundary conditions. The boundary conditions are usually specified in terms of the variables, the primitive variables, which are velocities and pressures. But here, the boundary conditions have to be converted into psi and omega, which is not as straightforward for different cases. Again, it depends on geometry, and it's only for structure and so on. These are because of all these problems. This method, though it is useful for 2D cases, cannot be kind of scaled for other complex geometries, or even for 3D, this cannot be directly scaled. That's when we moved on to solving these three equations directly using other techniques. We can still use the finite difference method. The major challenge here is when we understood the concept, like we wanted to do the same thing for this. So if you have, let's take a 1D equation to understand this difference. So if I just have a 1D problem where my continuity will reduce to dx of u equals to 0, and then my momentum equation will become, so let's say density is constant, and let's for now suppose ignore the viscosity term. So if I have just these terms like this, now if I have a 1D grid, so this is my ith cell, I plus 1 and I minus 1. So first concept is we till now what we were doing is we defined this, we discretized the domain, and then we defined all the variables at these discrete points. So if we do the same thing for these two equations, simultaneous equations that we need to solve for, so let's see what happens. So if I take the continuity equation and do a derivative at this particular point I, I'll use a central difference scheme. So that will give me ui plus 1 minus ui minus 1 by 2 delta x should be equals to 0. What this will end up with is ui plus 1 equals to ui minus 1. So if I have u0, every alternate term should be equal to each other. u0 should be u2 equals to u4 and so on. Similarly, u1 should be equal to u3 equals to u5 and so on. So if I have the boundary conditions such that even and odd are there, and throughout u is 0, if I have a boundary condition like that, then if we discretize the momentum equation, here we'll have u square, again the same equation, minus u square by 2 delta x should be equal to minus pi plus 1 minus pi minus 1 by 2 delta x. Here also you will get the same problem. We know that ui plus 1 and ui minus 1 equal, so this term will go to 0. This means pi will end up with pi plus 1 equals to pi minus 1. So the same problem happens where p0 should be equal to p2. All the alternate terms will be equal to each other. p1 will be equal to p3 equals to p5 and so on. So what this means is now I do not have any relation between p0 and p1. So if for suppose I can end up in a scenario where p0 is not equal to p1 and still have u, so if p0 is not equal to p1, and then I can have some like the coupling between pressure and velocity is kind of gone. If we know that if velocity is 0 throughout the domain, then my pressure also has to be constant. But what this equation tells me is only the alternate grid values have to be equal. There is no relation between I minus 1 and I. So this is with what we call the decoupling between pressure and velocity in case of collocated grid. So now the trick here is we use a staggered grid approach where we added two more grid points. These are our original grid, and then I added half cells, I plus half and I minus half. And then we do discretization in two different ways. The first discretization for the continuity equation will be done as usual, like before, for this cell. So discretization will be only done for this particular cell. So which will give me, instead of I plus 1, I minus 1, I will do the central differencing between the phases. So that will give me ui plus half minus u minus half by delta x equals to 0. So this will give me ui plus half is same as ui minus half. Because each and every phase will be included in this grid, so all the values of u will be 0. So this implies all u will be 0. And then for the pressure, I'll do instead of, if I do the pressure discretization also here, then I will also end up in the same problem like that. So what we will do is we'll do the staggered grid approach where the momentum equation will be discretized on a different cell, on this particular cell. So if I do that discretization there, so I'll have u square calculated at I plus 1 minus u square calculated at I by delta x. So these are the two cells minus pi plus 1 minus pi by delta x. We know that u is 0, so this term will become 0. And now I am ending up with an equation which is pi plus 1 equals to pi. So now all the pressures will be equal to each other. So this is what we actually needed. So whenever u is 0, we will end up with a scenario where all the pressures are equal to each other. So this is happening only if I do this staggering. So one will be cell center and another one will be phase center. The continuity equation will be solved on the cell center and the momentum equation will be solved on the phase center. That is the staggered grid approach. Then we discussed Mach algorithm, and once Mach algorithm is discussed, we moved on to finite volume method. So in finite volume method, the difference between finite difference and finite volume is basically when we have the differential form, we are not actually doing any kind of fun. So if I have an equation of the kind where, or let's take the steady equation. If I have an equation like this in 1D, let's say I have something like, so if I'm doing a finite difference form versus the finite volume. In finite volume, what we will do is we will do an integration across the control volume. And that integration, like once we do, again, if, we do it across the phases. So same as before. So we'll have multiple control volumes and then we define cell centers, phase centers, same as whatever we were doing before. And then we will end up with an equation of the kind APVP is sigma A and B phi and B plus P. This is the kind of equation we will be ending up with. And then from here, everything is straightforward. Like how do you solve for, like this is basically sum A times phi equals to P. So all you have to do is use a linear algorithm and then like the linear solver that we discussed before, and then you will be able to solve it. As long as the equation is linear in nature, which means that u value has to be known to you. If u value is specified to us, then we will be able to solve this as a linear equation. And then comes the problem. In Navier-Stokes, what we have is not linear in nature. So which means you'll have something like you have two equations. One is the continuity equation, which is del dot u equals to 0. I can write it as d times u equals to 0, where d is a matrix of which kind of is an operator basically that does the divergence operator. And then we have the momentum equation, which can also be written as some a times u plus some b times pressure equal to 0. The only problem here is if u is the variable that I am solving for, then the coefficient matrix itself is also a function of u. So we have to solve this set of equations, which is actually the main problem. So, and then of course in some cases we also have time derivative, then we'll have a du dt term coming here, but let's not go in there. So if I have only these two equations, then how do I solve this set of equations? So this is a nonlinear equation. So for any nonlinear equation, you have to start with some guess u star and p star, and then we have to progressively iterate until we reach the final solution. So the iteration will be like you in simple, what we do is you start with a given p star, like you have an u star. So you use the second equation first. So first step is based on U star, you calculate your A matrix, which has fluxes, derivative like the fluxes, diffusion coefficient, all those terms will be there in my coefficient matrix A. So first I'll calculate A at U star times I'll solve for U plus B times I already know the P star value. So this equation can be solved, and from this you will get a value of U double star. So first you will get an estimation of velocity, and this velocity estimate is not divergence free. So I have to come up with a velocity field that is divergence free. So I'll call that velocity as U tilde, which is a divergence free, which is whatever estimated velocity I have, plus I have to do some correction to it. And for that corrected velocity, there will be different pressure. So let's say that pressure as P tilde, which is whatever pressure I am currently having, plus some pressure correction P prime. I know that both of these velocity and pressure have to satisfy my momentum equation. So I will take the equation as AU times U double star plus B times P star should be 0. And the new pressure, and sorry, this is also U star. Note the notation here, I'm only using U star. I'm not using the updated value of velocity. I'm using the value of A, which is calculated before the update. So whatever is the initial guess I have taken, that is the coefficient matrix A. Instead of U double star, now we'll have U tilde. B matrix is doesn't depend on anything. This is just a constant matrix times P tilde equals to 0. If I do if I subtract second from the first equation, I'll have to subtract these equations. I'll have A U star U prime plus B P prime equals to 0. And now there is some simplification. In simple algorithm, what we will do is we will write U prime as, ideally we should be writing something like this, but calculating this is time consuming. So that simplification is we will write U prime as, anyway we are iterating step by step. So each step doesn't have to be accurate. So the idea is we will do some simplification here, and then we will use an under relaxation so that we are not overestimating it. So what we will do is we will replace this with only the diagonal elements. So this is with respect to the momentum equation, but the main criteria is we need to satisfy the divergence conditions, which means I also need to satisfy the d times u tilde should be 0, which will give me d times u double star plus d times u prime should be equal to 0. So this is the main equation that needs to be satisfied. So I have the equation for u prime that I can substitute here. So du double star will be, and from this I can solve for p prime. Once I'll have p prime, then I can substitute this here, get u prime. And then once I have u prime p prime, I can substitute this, get u tilde p tilde, and I'll check whether this u tilde, so now I'll have u tilde and p tilde. Now I will update my coefficient matrix. So now I will do a times u tilde plus b times p tilde. I will see whether this residual that I'll be having is less than my tolerance or not. If it is already satisfied, then I don't have to go ahead. If this is not satisfied, then again we will have to do the same thing. So the if if it is greater than the tolerance, then we will say u star is whatever u tilde I got, p star is whatever p tilde I got, and from there again the loop repeats. This is a simple algorithm. There are other simpler and simpler questions. The difference here is how one difference is here we started out with the p prime and then with p star and then updated my velocity from there. In simpler, what we will do is just opposite. So you will take the velocity field. So you will know the u value. You will calculate p value from there with a little adjustment to the matrix. Say you will do an plus and minus of identity matrix and then you do a little operation here. In simplex, what we do is one of the major approximations here is this one in taking the diagonal matrix. Because we are taking diagonal matrix and ignoring the neighboring terms, we are kind of overestimating the velocity correction. So we are overestimating here and this will get added up into here. So the pressure correction that you are estimating here will be higher than what is actually needed. So we have to do an under relaxation. So we'll not actually use, so when you do this update, you don't actually do like that. Instead, what we will do is we'll use some kind of reduction, something like this. So we have to under relax it. So you'll increase the number of iterations. So instead of that, in simplex, what we do is we will use another variation where this will also be replaced with a slightly different version, and that will kind of give you faster conversions. Like that will ensure the consistency is there. That is with respect to simple, simpler, and simplex. We also discussed several coding and we also given examples also in this particular course. Yeah, but this pretty much summarizes whatever we discussed in this particular course. For people who want to extend from whatever is already discussed in the course, the next step would be to move to unstructured meshes. So all of this is like nothing changes here. The only difference is in the equation here I've just written east and west. When you have an unstructured mesh, you have other terms. And then what happens when you have a non-orthogonal grid? So where here if you see the normal to the face and the line joining the centers of these two cells are the angle between them is 0 degrees, or you can also say the face and these are like 90 degrees. So these are orthogonal things. You can also have geometries where the mesh is not aligned completely. So you'll have non-orthogonal meshes also. So what happens in that particular case is also something that you can, whoever is interested can actually explore those concepts also. Yeah, so these are the things that we discussed in this particular course. If you do have any particular questions, we can discuss them. Otherwise, I think thank you all for joining the sessions. And if you do have any feedback, please do fill in the feedback form. Yeah, thank you all, and best of luck for your exams.